It's 3-8. I hope you're feeling great. We're looking at implicit differentiation. So again, still with derivatives. One more section after this with 3-9, but implicit, meaning that it's not explicitly written. So there's a few things that we're going to talk about. Wanted to discuss some of these new scenarios that we're going to see, and that is of functions that we are asked to take the derivative of. But when we're given those equations of the function, are we restricted to just having that explicitly written? Let's take a basic circle, for example. If you recall, x squared plus y squared equals, let's say, 9. That would be a center of 0, 0, and a radius of 3. If we had a circle like that, should we be able to find the derivative or rate of change on it? Well, normally we just say, well, yeah, we do a power rule, or what do we do with this? Constant, we know that goes to 0. So remember the GeoGebra slides that I went over at the very beginning of calculus with you all, just showed you what it meant to be the slope of a tangent. Geometrically, we talked about we can find that tangent at any point, but what would we have to do in order to find it? That we did not, because we didn't have that knowledge yet. So let's explore that scenario and see what we get. If I gave you that equation, I asked you to find the derivative of it, what would you do first? What do you think? Most of you probably would have done that. Subtracted over the x squared, and then taken the square root of our y squared that was left. Don't forget, you have to put the plus or minus. And then when you took that square root, remember, because there was plus or minus, you could not take the square root of each individually. I've proven that many times over to people. If I gave you 9 plus 16, if your life depended on the correct answer, you would say, hold on, let me ask Siri. No, you would hopefully just say 25. So you know that this is a true statement. So if I then took the square root of both sides, which you know that we should be able to do, it should still be equal. But if you took the square root of that and that individually, you would get 3 plus 4, which now you're dead. Remember, if I did do this, I would get a 25 in there, and now you would have a true statement still. So no, we cannot just take the square root of each thing individually. Be careful with that when adding or subtracting. Multiplying or dividing, it's all good. We were tasked with finding the derivative, differentiating this original, what is called implicitly written, not explicitly written equation. And the problem is we got this plus or minus in front. There's actually two cases that we would have to take the derivative of. And we'd have to rewrite this square root as a 1/2 power. And now it's a power chain rule, and we're going to have to do it for both the positive and negative. Ugh. We can do it, but I don't want to have to do that because I've done all this work and I've done nothing that they asked for yet, which was take the derivative. And of course, this is just a simple circle. What's going to happen when we get more involved in more complex equations or functions? It's not going to be fun. So that's where this thing called implicit differentiation was created. You know what? I'm not going to do that, even though I can. I'm simply going to do what was asked, and that is take that original function and find the derivative of both sides with respect to whatever letter they ask for, typically x. Not always, but typically. So that means you got to be careful here. This is where students start messing up with this. You got to look at these as power chain rules. Now, I know that when I take the derivative with respect to x of an x, it's all good. You don't have to think of it any differently because that's what we've always done. The derivative of x squared is and always will be 2x. But the derivative of another letter squared is not just always going to be a power rule. It is now a power chain. And if you remember that last section, 3.7, for the inverse trig, I did this already with that proof for inverse sine and its derivative. So we're going to do this again where we say it's plus 2y to the first, but we also got to take the derivative of the inside. And you're like, well, could we also do that with the x? Yes, but it's just not necessary because the derivative of x with respect to x is just 1. So we still just get our 2x. But here, we have to take the derivative of the inside, the y, with respect to the x, which rather than writing it as y prime, which looks really close to this, which is why oftentimes I won't even write y to the first. I don't want to get it mixed up. So I will write it as dy dx, and I'll oftentimes put parentheses around it so it's even more clear to see that, oh, by the way, that's what they wanted us to find. They wanted us to find the derivative of y with respect to x. Now, don't forget on the other side, a lot of students will make the mistake of putting a 9 there. They're just overlooking it, moving with the variables and forgetting about this constant. We know the derivative of a constant with respect to any variable is going to be nada, nothing, zero, zilch. So then what's left for us to do? What we've practiced for many, many years in algebra, and that's solving for an unknown. So I'm going to start by subtracting over the 2x to both sides so that that cancels out, and now I just have my 2y dy dx equals 0 minus that is that. And then what's being done to my thing that I want to solve for, my dy over dx? It's being multiplied. So I'll undo that by dividing by 2y. And now I have my dy dx, and it's equal to, since these are multiplying, I can cancel and make it even better as negative x over y. And if you really understand what that represents, tell me graphically, or talk to yourself since you're talking or looking at a computer. Dy over dx, remember, is the slope of a tangent. Where? Anywhere. At any point. And give me the x and the y, and I now can tell you for this circle, we would have that. And just to throw this out there, what if I changed it instead of 9? What if I changed it to, say, 49, a radius of 7? Would that have changed anything? Well, no, the only thing that would have possibly changed would have been this, which, since it's still a constant, it's still 0. We would get the exact same slope. It just would have been a bigger circle. All right, so that, my friends, is called implicit differentiation, which allows us to skip solving it for the y in terms of x and then doing the derivative. And that was a lot quicker and easier than doing all of this and then having to rewrite this whole thing as a 1/2 power and doing not only once but twice the power rule with a chain. That was pretty quick and easy. So as I mentioned, not a whole lot to this section. It is all about that implicit differentiation, and I just showed it to you by example so that we don't have to write our equation explicitly. In other words, solve for one variable. Now we're going to use this implicit differentiation that allows us to still find that thing without the hassle. So I just wanted to give you 3 things to leave you with, and these are how to attack an implicit differentiation problem. And that is, first and foremost, find an equation, if it's not already given, relating the unknown values, typically our x and y. Then differentiate both sides with respect to whatever they ask you to, typically, again, our x value. And as a warning, remember, do not write it as y prime, but write it as dy over dx. It's easier to lose the y prime than it is the dy over dx. And lastly, if they ask you to take the derivative or differentiate, then that means you now have to solve for that dy over dx by isolating it and sometimes even factoring it out. That's it. Of course, we can use this for our applications of velocity acceleration, but the only way that we're going to get better at this is by doing it correctly. More times, the better. Right? Let me know if you have any other questions concerning this. Otherwise, keep working hard. One last section left in chapter 3, and then we'll move on to chapter 4. Take care, everyone. See you real soon.